Check this out. We've got something really fun today. This is so amazing. Oh man, again? 11.1 and 11.2, counting methods. We'll start off with the fundamental counting principle. I used to live in Airdrie. To get home from Calgary in good time, I can take Stony Trail, Métis Trail, or Deerfoot Trail. These all lead to Balzac. From there, I can continue on the QE2 highway, or I can take Range Road 11. Using these routes, how many ways can I get home? Let's draw this out. Airdrie is in the north, Balzac in the middle, and Calgary down here. Almost like somebody planned that. We've got Deerfoot Trail, we've got Métis Trail, and we've got Stony Trail. From there, I can continue on the QE2 to Airdrie, or I can take Range Road 11 to get there. How many ways? We could count it up. Taking this first path, we've got 1, and then still on the first path, we've got 2. Second path, we've got 3, and second path, second option, we've got 4. And third path, 5 and 6. So you can see that there's 6 ways. There might be an easier way than just counting, and if the problem was any more complicated, we wouldn't want to be counting up lines like this. We could easily lose track. So if there was 37 options to get from here to here and 42, that wouldn't be very nice. So for each one of these, we've got 2 options here. So really we could write this as 2 plus 2 plus 2, or that's also kind of long. We could just write 3 2's to get 6 ways for me to get home. Let's say I have 3 shirts, 2 pairs of pants, and 2 hats. How many outfits can I create if I must wear one of each? So I'm going to use these, rearrange them to show I could wear this black shirt, I could wear this red shirt, or I could wear this dark blue shirt. With the black shirt, I could wear the blue pants, or I could wear the gray pants. And I'm going to fill all this in with these little pictures here. See if you can find the answer and then start the video. So it looks like when I arrange all my options here, I have 12 options. So I could wear any one of these 3 shirts. For each of these 3 shirts, I have 2 options here of pants. And for each of these shirt-pant combinations, I have 2 hats that I could choose from. So that gives me a total of 12 options. But if this question was really long and I had 37 shirts and 5 pants and 22 hats, I wouldn't want to be drawing it out here. So again, I've got 3 shirts, and then I've got 2 pants, and then I've got 2 more hats. So 12 options. And this is the fundamental counting principle. If there are n ways to perform a task and m ways to perform a second task, then there are n times m ways to perform both tasks. Now that's assuming that they're independent of each other. Use when you're choosing one item from a set or groups. Here's an example. At a restaurant, there are 8 drinks, 12 appetizers, and 32 meals to choose from. We wouldn't want to have to draw this out. If we wanted one of each, how many unique combinations could we make? So using the fundamental counting principle, there's 8 ways to choose a drink. There's 12 ways to choose appetizers. And there's 32 different ways to choose a meal. And we just multiply those together, and we get 3,072 different meal combinations. Now, that all might seem very easy. The problem is that questions are always word problems, and they don't tell you whether it's fundamental counting or not. So let's look at these 2 examples here. A multiple choice test has 10 questions, each with 4 choices, A, B, C, D. How many ways could I randomly answer the questions? So in this one, we have 10 questions. So I'm going to make 10 blanks here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And for each of these, think, how many ways can I do this first thing? Well, there's 4 different ways I could do the first thing, A, B, C, or D. So I'm going to say 4. How many ways can I do question 2? Well, it's also 4. How many ways can I do question 3? And so on. And they're all 4 because they all have 4 options. And what do? We're going to multiply each one of these because that's the fundamental counting. And this is, we're choosing one way to do this and then one way to do this. So they're independent, and we can use the fundamental counting principle here. So this is really 4 to the power of 10, or 1048576. Okay, what about a group of 10 football players are shaking hands? Every one of them must shake hands with everyone else. How many handshakes will occur? So think about this one, try to figure it out. Pause the video and restart the video when you think you have it. So I drew 10 football players here, and they're all ready to shake hands. I'm going to start with this guy here, and he shakes hands with 1, 2, 3, 4, 5, 6, 7, 8, 9 people. I'm going to move on to the next guy, but I'll change the color here. So this next guy, he's already shaken hands with the first guy, so that doesn't need to be repeated. He needs to shake hands with 1, 2, 3, 4, 5, 6, 7, and 8. And so on. So the next guy, he'll just need to shake hands with 1, 2, 3, 4, 5, 6, 7. So each of these guys have one less hand to shake. So this would be 6, 5, 4, 3, 2, 1, until we get to the last guy who actually doesn't need to shake anyone's hand because everyone's already shaken his hand. So here's how many handshakes we'll have. 9 plus 8 plus 7 plus 6 plus and so on. Now this is not the fundamental counting principle because we're not choosing one thing out of a group. So we add all these up and we get 45. Now this also could be a arithmetic series. So let's do that as a reminder. We've got Sn is equal to n, t1 plus tn divided by 2. So in our case, we want to do S9, although we could do S10, but the 0 wouldn't make any difference. So our n here is 9, our first term is 9, our nth term is 1, and then we're going to divide by 2. And this also equals 45, of course. On to word games. We're going to use the approach that was introduced by a mathematician named James Tanton. And I'll put a link to his videos below. If you'd rather listen to this in his nice Australian accent, then you can do that. But he has this approach where we learn pretty much a strategy that will work for any question. So you'll never get stuck, and I like that. It helps you understand the math rather than the textbook's way of introducing 2 separate ideas and trying to apply formulas to either case. We will get to that, but first, let's understand the math. How many ways can we arrange the letters in the word gym? So we could start off with just J-I-M, and we could switch the last 2 letters here and still start with J. Now we could give somebody else a turn to start first, so how about I first and then J-M, and then I and M-J, and then last M never got a turn to start, so could be M and then Ji or M I-J. So it looks like there is 6 different ways to arrange these 3 unique letters. What about using the fundamental counting principle? Think of each position here as a thing to do. Now we have 3 letters, so we have 3 ways to fill this first position. Now once we use up a letter, we only have 2 ways now to fill this second position, and once we've used up that, we only have 1 letter left and it has to go last here. And this is the fundamental counting principle because we're choosing one thing. There's 3 ways to do this thing and we're choosing one of them. Then there's 2 ways to do this and we're choosing one of them. And there we go, and this would be 6 ways as well. Now I do have this big long explanation here if you didn't like the way I said it. But anyways, there's 3 ways to fill the first position, 2 ways to do this, and 1 way to do the last. How many ways can we arrange the letters in each of these words? Pause the video, give it a try, and start when you think you got it, then you can just check your answers. Otherwise, if you're having trouble here, house is 1, 2, 3, 4, 5 letters. So we have 1, 2, 3, 4, 5 spots. For the first one, we have 5 letters to choose from. And then once we use up 1, we only have 4 left, and then 3 left, and 2 left, and 1 left. So 5 times 4 times 3 times 2 times 1 is 120. The next one has 4 letters here. So 1, 2, 3, 4. We've got 4, 3, 2, 1 ways to do that. So 24. The next one, 1, 2, 3, 4, 5, 6, 7. So we got 7, 6, 5, 4, 3, 2, 1. When we multiply those out, we get 5,040. This one has 6, so 6, 5, 4, 3, 2, 1, 720. And unglamourized, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12, 11, 10, 9, 8, 7, 6, 5, 4. Okay, now that's a lot of numbers, but we get 479 million, 1,600. All right, now subdermatoglyphic has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So we would have to write 17 times 16 times 15 all the way down to 1. And that's not fun anymore. So there must be a better way. And they're called factorials. And they're exclamation marks. It's not 1 yelling, it's 1 factorial. Now that means you multiply all the whole numbers from the factorial number down to 1. So 1 factorial is just 1 because it's already at 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. And see, you go from that number there all the way down, just the whole numbers, down to 1. So 5 factorial is 5 times 4 times 3 times 2 times 1, 120. We don't want to write this out every time. We just can use the factorial symbol here on a TI-83 or 84. It's under math, then probability, and then number 4 is where you find this factorial sign. So you can just type in your calculator 6 factorial, and you get 720. 7 factorial is 540. And so subdermatoglyphic from the last slide can be written as 17 factorial, and that's a lot easier, and we could actually get that number if we wanted it. Now there are a couple more things we can try with our calculator, and that's 0 factorial, which is equal to 1. Now we'll talk about y later, but that equals 1, and if you try any negative number in your calculator, it's not going to give you an answer because it's undefined. Remember, we defined this function, we made it up. We defined it as going from the whole numbers down to 1. But if we're already below 1, that doesn't make sense. Although again, this is a special exception we'll talk about later. Here's a fun question. What is the largest factorial your calculator can handle? So give it a try, and also try your phone. You might have to turn your phone sideways to get the additional buttons. Now, if you're running a TI-83 or 84, it actually tops off at 69 factorial. Now, ironically, your phone will do better. If you have an iPhone, then it typically tops off at 103 factorial. At least it has for the last few years. If you're running an Android, it can differ quite a lot. Androids start topping off at 170 factorial, but we found one that would go all the way to 28,000 factorial. So I guess we see who the winner is here. How many unique ways can we arrange the letters in the name Bob? Now, all our previous examples had unique letters, but Bob has two B's that are indistinguishable. They're not unique. So if they switch places, we don't get another arrangement. When we were doing this normally, we would just say 3 factorial. And that gives us 6, and that's just too many. So we want to adjust it for the two B's that are in this word here. Now, if we could label them so that they're different, then we would see that there are 6 different arrangements here. But this Bob and this Bob is not really a unique arrangement. So we're going to have to divide. We divide by how many ways are there to arrange the identical letters. So there's 2 B's, so there's 2 ways, or 2 factorial. Now 2 factorial is 2, so either way it's 2. So we divide by 2, and there's only 3 ways. Now this one's really easy. You could see the 3 ways: the O first, the O second, or the O third. But let's try a more difficult question. How many unique ways can we arrange the letters in the word SAS? Now normally if we had 4 letters in a word, then there would be 4 factorial ways to arrange those letters. But in this case we've got 3 S's and they're all identical, so if they switch places I can't tell, and we wouldn't get another unique arrangement. So I've got to divide off the number of ways that we can arrange the S's. Now since there's 3 S's, then they can be arranged 3 factorial times. Now 4 factorial is 24, and 3 factorial is 6. So there should be 4 different ways to arrange SAS, and actually that makes sense. The A could be first, the A could be second, third, or fourth. Let's take a visual. I actually labeled all the S's and made all the possible arrangements here, just so you can see why we're dividing by 3 factorial. So the first row here is where A is first, and then there is 1, 2, 3, 4, 5, 6 ways to arrange the S's. And that's where this 6 comes from, or the 3 factorial. It's much easier to remember. And each time we do that, there is 6 ways to arrange the S's. So we've got 24 ways total, but we're going to divide it by 6 and just get 4 unique ways. Let's try these examples here. These are words where they have a repeating letter. So for the first one, how many ways to arrange these 4 letters? So that would first be 4 factorial to rearrange 4 letters. But we've got 2 S's, and them switching won't make another arrangement. So we've got to divide by 2 factorial, or just 2. And this one, when we multiply this out, we get 12 different ways to do that. Let's try cheese. We've got 1, 2, 3, 4, 5, 6 letters, so 6 factorial to arrange 6 letters. Now we need to divide off the ones that aren't going to give us another arrangement. We've got 3 E's, and arranging 3 E's in different ways doesn't give us another arrangement. It just looks the same to us. So we need to divide by 3 factorial. So we got 6 factorial divided by 3 factorial is 120. Next is Samsung. Samsung has 7 letters, and it's got 2 S's. So we want to divide by 2 factorial. So this is 2,520. And last one on this page, factorial. Factorial has 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. And we've got an A here, and we've also got an A here, and nothing else is repeating. So we just need to divide by 2 factorial. There are 2 different ways we could switch the A every time and not really get a new arrangement. And that would be 181,440. Now let's step it up a bit to words where we have more than one letter being repeated. Our first step is going to be the same. We've got 6 letters, so there is 6 factorial ways to arrange 6 letters. But now we need to divide by How many ways can the e's switch and the t's switch? Now this depends on the fundamental counting principle. So the e's can be arranged in 2 factorial ways, and the t's can be arranged in 2 factorial ways. And if there's 2 ways to do this and 2 ways to do that, then we're going to multiply them. So in this way, the total here is 2 factorial times 2 factorial, or 4. But I'll just write 2 factorial times 2 factorial, so you get the pattern. Now when we multiply that out, we get 180. Let's try cheesiest. So cheesiest has 9 letters, so 9 factorial ways to arrange those. And then let's look for the repeating letters. We have 1, 2, 3 e's, and so that means that the e's can be arranged in 3 factorial ways. We also have 1, 2 s's, and those s's can be arranged in 2 factorial ways. So put together, the e's and the s's switching around is 3 factorial times 2 factorial. Now we can multiply that out and we get 30,240. How about notation? So notation has 8 letters, so there's 8 factorial ways to arrange 8 letters. Now let's divide off the ones that repeat. So we got 1, 2 n's, so that would be 2 factorial. We also have 1, 2 o's, so that will be another 2 factorial, and we have 2 t's, so that would be another 2 factorial. And that's all fine, we just put them all in the denominator and multiply them. And when we multiply this out, we get 5,040. Now check this out. I'm going to do a little bit extra here. Say you were just analyzing this and looking at 5,040, you might remember that that's 7 factorial. So how is this 7 factorial when we got 8 factorial divided by 2, 2, and 2? Let's just take a quick look at that. This would be 8 factorial divided by 2 factorial is just 2, 2 factorial is just 2, and 2 factorial is 0. So this is just 2 to the power of 3, or this is 8. So if you think about this, this is 8 factorial is 8 times 7 times 6 times 5, and so on. Okay, divided by 8. And so what happened was the 8 was divided off, and all we're left with is 7 multiplied by each whole number down to 1, which is 7 factorial. So that's kind of cool that that number showed up there. Let's try alfalfa. So alfalfa has 7 letters, and we've got 1, 2, 3 A's, so that's going to be 3 factorial. We've got 2 F's here, so that's going to be 2 factorial. And we've also got 2 L's, so another 2 factorial. So in this case, we've got 210. Now let's do a little something like this. Maybe we want to think about this without a calculator. It's pretty easy to type this in a calculator. Remember the brackets around our denominator, or divide by each one of these separately. But what if we didn't want to use a calculator? Let's just see what we got. We got 7 factorial, so that's 7 times 6 times 5 times 4 times 3. I don't want to write out the rest, so I'll just end it there. And what about this 3 factorial? You know what? If I just line those guys up, they'll just cancel out. And then I'm left with 2 and 2, because 2 factorial is just 2. So 2 times 2 is actually just 4, so those can cancel out as well. So really, this is just 7 times 6 times 5. Or maybe it's easy to do. 6 times 5 is 30, times 7 is 210. So we can break these down, and using some tricks, do them without a calculator. Okay, let's do the last question. Cheesiest. Yes. It's got 13 letters. Next, we've got to figure out which ones repeat here. We've got 1, 2, 3, 4 E's. So that's 4 factorial. The next thing we've got is S's. We've got 1, 2, 3, 4 S's. So another 4 factorial. And then the C and the H and the I and the T and the, okay, they don't repeat, so we're done. We put this in our calculator. And the numbers start getting so large that it's actually kind of nice just to express your answer like this. But in this case, it's 10,810,800. Now, let's go back to the word better and look at it again and also discuss why 0 factorial has to be 1. So for the word better, we had 6 letters. And, we had 2 E's, okay, and we also had 2 T's. So this is how we wrote it before, and that's great. That's how we want to write it. But just so we can understand what's really going on here, we also have 1 B. So actually I'll write this as E and this is T, and we also have 1 B. And we have 1 R. And if you add up these numbers here, 2 plus 2 plus 1 plus 1, it equals 6. So the numbers down here actually have to add up to this number here when we're doing this type of question. Now, it also makes sense then that we could do the other letters, like A. How many A's do we have? Well, we have 0 A's. We have 0 Z's. We have 0 P's. And all the rest of these are just 0, and our rule still works. We can add up all of these plus as many zeros as you want, and it will still get 6. So 0 factorial is 1. Why? To make these work. So man invented this function, and so we just said, hey, it's got to equal 1 so that our math will always work. Now I'd like to share with you my favorite joke, and it goes like this. How does a mathematician put out a house that's on fire? Well, he dials up the fire department and they come and put out the house fire. Okay, how does a mathematician put out a match, a lit match that's on fire? No, he doesn't blow it out, no. He takes the match and lights the house on fire, thus reducing it to a previously solved problem. Yes, thank you. Okay, how many ways can we arrange the letters in this? Now, this isn't a word, but we still have letters. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 letters. So that would be 12 factorial. Now we divide by how many A's there are, factorial, and B's, 4 factorial, and C's, 5 factorial. So we can get that this is 27,720. Now let's see what we can do with, this is called labeling. Mr. Muckins is a professor who needs to assign 12 students in his class letter grades, and he decides to give out 3 A's, 4 B's, and 5 C's. So how many ways can he do this? So first of all, let's make 12 students. There's 2, 3, and now we're going to give each of these students a letter. I could give this one an A and maybe this one, and how about this one? And 4 B's, so I like this guy here, and this girl here, and this girl here, okay. And this guy here. And the rest C's, these guys over here, all right, they're all C's. Now how many ways can I rearrange these? Well, it turns out to be just like this previously solved problem. I've got 12 letters here, and 3 of the same, 4 of the same, and 5 of the same. And this actually is just the same problem. It's just the word problem here and just a word game here. Let's try another word problem. There are 10 people in an office. 4 of them will be selected to work on a committee. I mean, 6 of them will not be. So we could say that the people that are going to be working on a committee, we'll call them C. C for committee. And then we need another letter like N, not on the committee. And we're going to have 4 people on the committee, so 1, 2, 3, 4. Then we're going to have 6 people not on a committee. 1, 2, 3, 4, 5, 6. Now, how many ways to rearrange these letters? See, we took this word problem and we just made it into rearranging letters. So this would be 10 factorial, 4 factorial, and 6 factorial. And so if you wanted the actual number, this would be 210. So in general, if we have n items being arranged, then A of them will have label A, B of them will have label B, and so on. And this will be our formula. 4 students will get to go to Tim Hortons out of a group of 14 eager volunteers. How many ways can these students be chosen? Well, let's call the 4 students here, we could call them T for Tim Hortons, so 3, 4. And then the other 10 students, we'll call them L for losers, because they didn't get to go. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many ways to rearrange these letters? So we've got 14 factorial, we've got 10 L's, and 4 T's. And if we wanted the number, it's 1001. 15 horses run a race. How many ways can they come in first, second, and third? Now, if they mention these positions, then we're going to have to assume that they're distinct. It doesn't just say the first 3 winners. It says first, second, third. So let's call the first one F, the second one S, and the third one T. And the other 12 horses we're going to call 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 losers. And to figure out this one, we've got 15 factorial divided by 1F, 1S, and 1T, which you don't need to write because they are just 1, but I'll just do it there just to make sure we've got everything. And then all 12 of these losing horses. And this equals 2,730. I have 4 Twix, 3 Kit Kats, and 2 Mr. Big to give out to 9 students in a class of 20. How many ways can this be done? Now we start to get a lot of students here, so I'm not going to write out all the letters. But you can see that if we have 20, that would start off with 20 factorial. We've got 4 Twix, so that will be 4 factorial. Kit Kat is 3 factorial, and Mr. Big is 2 factorial. And that's our 9 lucky students there. The other 11 unlucky students will not get anything, so that will be 11. They're all the same. If you didn't get anything, you didn't get anything. Okay, and we can multiply that out and get 211,629,600. These next questions here are pretty fun, but we don't tend to use these questions in this course. If we want to move from A to B, and we can only use movements down and to the right, how many paths are there from A to B? Now, we don't want to move left or up, because then we could just start going in circles, and then there'd be infinitely many paths, and we don't want to do that. So just down and to the right. So let's see what would happen. So this is one movement, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it took 10 steps to get there. Let's try a different path. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That took 10 steps as well. Let's go through the middle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So no matter what you choose, there's going to be a total of 10 movements. Now, what about the down and to the right? If you notice, no matter which path I took, I need to move 7 units to the right, and I need to move 3 units down. And I can really put those in any order I want. So really, I've got 7 R's and 3 D's, for example, and a total of 10 movements. So I can figure this out by going 10 factorial divided by 3 for the down movements and 7 for the right movements. And I can do these down and right movements in any order, but I need 3 downs and 7 rights. And so we get that there's 120 different ways to get from A to B following this grid. This was part of Permutations and Combinations 1, 2, and 3. We did the fundamental counting principles. We also did combinations and permutations, but we didn't do them by name. So next time we will identify them and show you the difference. But right now you can do most questions that come your way. So here's some questions, give them a try, see if you know what you're doing.